And the topic that has been allotted to me today is vaporizers, and I call it Vaporizers Demystified because I have tried to make it as simple as possible for the students. Because when I was a student not so long ago myself, I found this topic very difficult. So I'm very, very happy to be presenting it to you. So I'll start with the physical principles first. The first question that you should ask yourself when you start reading vaporizers is, what is critical temperature? Critical temperature is obviously the temperature above which a gas cannot be converted into a liquid. However, much pressure is applied. You see, a substance can exist in two phases. It can exist in a gaseous phase and it can exist in a liquid phase. Now, if the substance has to convert from the liquid to the gaseous phase, then, then that substance undergoes evaporation. But if you have to go the reverse way, that is, you have to convert the gas into the liquid, then you need to either increase the pressure or decrease the temperature. So there is a critical temperature above which the gas cannot be converted into a liquid, however much pressure you apply. And for water, it is 374 degrees centigrade. So that beyond this temperature, there is no water. There is only vapor, right? For nitrous oxide, it is 36.5. For carbon dioxide, it is 31.2. And for oxygen, it is minus 119. Now look at this diagram. In this diagram, I have also included the solid phase now, right? So when there comes a stage when a substance can exist in all three phases simultaneously, right? The solid can be converted into a gaseous phase and vice versa through sublimation. And there comes a stage where a substance can exist in all these three states simultaneously, and that is known as the triple point. So the triple point, there is a certain pressure called P3, a certain temperature called T3, which is indicated here on the slide. And that's all that you have to remember, the definition of triple point, because sometimes it's asked in MCQs. Now, what exactly is a vaporizer? I have broken down the definition for you. Remember, whenever you answer in an exam and you give a definition, now in a definition, every word is important. So if you have to remember a long definition, you break it up into little pieces. So a vaporizer is a device that changes a liquid anesthetic into a vapor, right? It adds a controlled amount. The important word here is controlled, because a very precise or a very controlled amount of this liquid anesthetic agent will be added either to the fresh gas flow or the breathing system or the carrier gas. And then this subsequent admixture will be delivered to the patient. So the vaporizer is a device which allows this to happen. So what does it do? It converts the liquid volatile agent into vapor, allows the admixture with the carrier gas in a controlled and precise manner. By this I mean that suppose you have set a certain dial setting, right, of 2% or 3%. So you would like to maintain this precise and controlled dial setting throughout your procedure, irrespective of the atmosphere and irrespective of the other factors involved. That is good balanced anesthesia. So this should be delivered to the patient in a controlled manner, and that is the exact function of a vaporizer. Now, some physical principles which you should know, and they are namely saturated vapor pressure, boiling point, heat of vaporization, specific heat, and thermal conductivity. I will discuss them one by one, and I will also tell you their clinical significance. So what is saturated vapor pressure? Let's look at this slide first. Now here you see that this is an open container, and vaporization is happening in this container. So the molecules are moving in and out, right? And there are two things that are happening here. Now, inside the liquid, there are cohesive forces that are keeping the molecules together. And outside, the motion of the molecules, or the kinetic energy of the motion of the molecules, is allowing the molecules to escape outside. So these two forces are at work together. Molecules inside, they are being held by cohesive forces. They are moving. Obviously, they have kinetic energy. And those which are near the surface of the liquid, they are popping out into the atmosphere, and they are evaporating, or they are being converted into vapor. Now, suppose I close this container. When I close this container, what will happen? That the molecules will move back and forth again and again, right? And a stage will come when the amount of molecules inside and outside will be in perfect sync. That is, the molecules leaving and the molecules entering the liquid will be exactly equal. So the space above the container here will be totally saturated with vapor, and that is what we call as saturated vapor pressure, right? So whenever you talk about saturated vapor pressure, remember never to use it individually. When you say SVP, you always mention the temperature as well. For example, because as the temperature is increased, right, more and more molecules are escaping, and the saturated vapor pressure also increases. So what is the importance of the saturated vapor pressure? Let's just go to the previous slide now. It's a very important factor governing the vaporizer design, right? When the molecules leaving the liquid and re-entering the liquid become equal at that temperature and at that pressure specific to the agent, this pressure is called the SVP. Now, the more the saturated vapor pressure, the more volatile will the liquid be, right? So, a higher saturated vapor pressure means that the liquid is more volatile. And different anesthetic agents have different saturated vapor pressures or different vapor pressures, because of which they require different vaporizers. So this is the concept that you have to understand. Next we come to boiling point. Now what is exactly boiling point? It is the temperature at which this vapor pressure or these vapors that were escaping becomes exactly equal to the atmospheric pressure. And when this happens, then the liquid begins to boil. When this happens, the liquid begins to boil. Now, one thing which you should understand is that what is the difference between evaporation and boiling? Now, remember, if I keep a glass in air for some time and I see it tomorrow, then there will be no water left in that glass if there was water previously. So what has happened? The water has evaporated from the surface of the glass. But what happens in boiling is that bubbles or bubbling occurs throughout the body of the liquid. So remember, the first difference between boiling and evaporation is that boiling or bubbling occurs throughout the liquid and evaporation occurs only at the surface of the liquid. So suppose at sea level, say 760 mm of mercury, water boils at 100 degrees centigrade. And suppose I go up to Mount Everest, right? I go on an expedition and I reach Mount Everest, and there the pressure is around 400 to 500 millimeters of mercury. So here the boiling point will come down and it will be around 70 to 80 degrees, right? So suppose you're trying to cook rice. You're trying to cook rice at sea level and you're trying to cook rice at Mount Everest, right? Or maybe at the base camp of Mount Everest. So there you will find that it is more difficult to do so. Now we come to the concept of volatility, right? So remember one thing, that the more volatile the liquid, right? It's very simple to understand and I've broken it up for you. The more volatile the liquid, the weaker will be the cohesive forces of the liquid and the lesser energy it will require to vaporize. So the speed at which a liquid vaporizes, remember, depends not only on its ambient temperature and pressure, which is obviously important, but also on its volatility, right? And remember, whenever the saturated vapor pressure is high, as I explained, the boiling point of the liquid will be low. So it is vice versa. Now, there are two other concepts that you have to understand, the last two physical principles, and these are the heat of vaporization and the specific heat. Now, what is the heat of vaporization? It is the number of calories which is necessary to convert 1 gram or 1 ml of the liquid into vapor, right? And for most liquid anesthetic agents, it is around 60 calories per. Now, what is the importance of this heat of vaporization? Whenever the liquid is being converted into a vapor, remember what is happening to the kinetic energy of the vapor. That is going down and down and down. And the body of the liquid then begins to cool down. So vaporization तो हो रहा है, लेकिन liquid cool भी होता जा रहा है. And because the liquid is cooling, what will happen now? The vaporization will become ineffective or stop or slow down, or the vaporizer concentration output will decrease. So the heat of vaporization keeps these temperatures stable. That is the importance of heat of vaporization. Now, about the specific heat. Specific heat is the quantity of heat which is required to raise the temperature of 1 gram of the substance, you can say, or 1 ml of the substance by 1 degree centigrade. Now, what is the importance of this specific heat? If I have a substance of high specific heat, what does it mean? It means that It is more stable for, it actually means that there is a gradual slower temperature fall. So the deceleration of vaporization is less and there is a better output. So copper is a good agent which is used in most vaporizers, and the reason is this, that it has a high specific heat and it has a high thermal conductivity. I'll just tell you what thermal conductivity is, and which is why copper is a favorite, and it was earlier initially also with the old vaporizers a favorite. So what is the clinical importance of this? It's important regarding the amount of heat supplied to the liquid and also the material used to construct the vaporizer. That is important when you are talking about heat of vaporization and specific heat. Now, what is thermal conductivity? Thermal conductivity is nothing but the measure of the speed with which heat flows through a substance. So if the heat is flowing fast, agar jaldi jaldi ja raha hai, तो it will equilibrate the temperature of the contents with the atmosphere at a more stable temperature, right? And that then again, copper is a very good, is a substance with a very good and a very high thermal conductivity. So the higher the thermal conductivity, the better the substance conducts heat. So I have highlighted the clinical importance of all the physical principles which you should know when you read about a vaporizer. Now with that background, let's talk about volume percent. Now, what is partial pressure of a gas? Obviously, we know the Dalton's law of partial pressure. We talk about volume percentage. We know that the Dalton's law of partial pressure means in a gas mixture, the sum of the partial pressures of the individual components of the mixture is the total pressure. That is the Dalton's law of partial pressure. Now, when we talk about 21% of oxygen, right? In 760 mm of mercury, it is different from 21% of oxygen in 500 millimeters of mercury, because the partial pressure of oxygen at 1 atmosphere is 160 and at 500 millimeters of mercury is 105 millimeters of mercury. So whenever the ambient pressure comes down, remember, and the concentration is the same, when the ambient pressure comes down and the concentration is the same, I'm not able to see this slide. So the Dalton's law of partial pressure states that, I've already told you what that is, and you know that 21% of oxygen exerts how much partial pressure at sea level. How will you know that? So in order to know that, you will just take simple maths. This is 760 into 21 divided by 100, and this will give you roughly 159.6 or 160 millimeters of mercury, right? You can look upon this the other way. You can approach this from the other direction. If you know the partial pressure, that is around 160 millimeters of mercury, and you have to find the percentage, you can divide it by the atmospheric pressure into 100 and you will get 21%. Now, these calculations are important. If I ask you that in a bottle containing halothane, you have to calculate the percentage of halothane above this liquid level. Suppose I ask you, this is a bottle of halothane, and tell me how much halothane is present above this liquid level. So we know that at 20 degrees centigrade or around at room temperature, the saturated vapor pressure of halothane is 243 millimeters of mercury. And if the atmospheric pressure is 760 millimeters of mercury, then the volume percent here will be 243 divided by 760 into 100. And this will come as 32%. So the percentage of halothane above this liquid level is 32%. This is a slide I will show you time and time again, because you have to learn how to classify vaporizers in these points, right? The method of vaporization, the regulation of output, the temperature compensation, the agent specificity, plenum or draw over vaporizers, and the location, right? So now I'm going to talk about the method of vaporization. So the method of vaporization can be basically of two types. It can be flow over. I'll explain them in detail one by one. It can be flow over. It can, as in tech vaporizers, which we use nowadays, independent vaporizers, Vapor 19.1 vaporizer with wicks, and in the Goldman's vaporizer without wicks, right? Then bubble through, which all of you know is the copper kettle. It is a purely bubble through vaporizer. The Boyle's bottle, it's a nice, ingenious way where you can use both flow over or bubble through. And you can use both these methods of vaporization in the Boyle's bottle. And lastly, you have the injection vaporizer, which is Desflurane. Everything will be discussed subsequently. Now let's just look at the Boyle's bottle. Now about the Boyle's bottle, if you see the Boyle's bottle over here, you will see that there is a lever, right? And this lever, when it is in the down position, then the entire gas, right? It's just passing through the bypass chamber. And when the lever is in the up position, then the gas passes not through the bypass chamber, but slowly it passes through the vaporizing chamber. Now, inside the Boyle's bottle, you have this diagram. You have this. Can you see this cowl here? Right. This is a cowl. You can see it here. It's very clear over here, and it's connected to a plunger. So when you move this plunger downwards, right? When this plunger comes downwards, then more and more of the liquid enters the vaporizing chamber and it bubbles through it. So from flow over now, it becomes a bubble through vaporizer. So by using the plunger, we can convert this Boyle's bottle from a flow over into a bubble through vaporizer, which is very useful. So this is about the Boyle's bottle. If you try to classify it, it is obviously a flow over without wick or a bubble through vaporizer. That is the method of vaporization. It is a variable bypass and it has no temperature compensation, right? So, you know, there are two bottles in it, ether and trilene. You must have seen it on your old Boyle's too. And the ether bottle has a broader and a narrow base, the other agents. That is how you identify the ether's bottle. And why this happens is that it's just basic physics again, that the higher the blood gas solubility, the more of the concentration required initially to achieve a proper anesthetic inhalation. And for that, you require a larger surface area and therefore a larger bottle, right? So here, obviously, you don't have any temperature compensation. So what will you do? You will keep wiping the bottle or you can cover it with a warm Gamsine. And agent specific, it is a multi-agent. You can see, you can use various agents through it and it can be used in and out. Now, again, so I spoke to you about method of vaporization. Now, how to regulate output concentration. This is something basic that you have to understand, and I'll explain it very clearly. So you will never confuse between what is variable bypass and what is measured flow. There are two broad categories, remember. There is a variable bypass vaporizer and there is a measured flow vaporizer. The best example of a measured flow vaporizer is a copper kettle. The rest of the vaporizers you are using are invariably variable bypass vaporizers, right? So this can be with either a fully saturated vapor chamber, as in a TEC or a Plenum Vapourisers, or an electronic Aladin cassette, which also I will explain to you very well. Or it can be a variably saturated vapor chamber, as in a Boyle's bottle or a Goldman vaporizer. So remember this diagram, right? This is a very basic diagram that you have to remember, and it will come up time and time again in every vaporizer. Just remember that gas is entering from the inlet and it is basically passing through the bypass chamber, right? And then some amount of gas will also pass through the vaporizing chamber. So suppose vaporizing chamber of sevoflurane contains 21% gas. Now, if the gas comes inside this inlet, grabs up all this sevoflurane or halothane or whatever agent is here, and then enters out, then just imagine a very lethal amount of anesthetic agent will be delivered to the patient. So what is the main purpose of the bypass chamber? The main purpose of the bypass chamber is to dilute the lethal amount of vapor that is coming out of the vaporizing chamber. So this is simple and you should just fix this in your head. For example, vaporizing chamber of sevoflurane contains 21%, but MAC is almost 1.9%, and fresh gas from vaporizing chamber is diluted by gas through the bypass chamber. As you can see here, the gas is entering. It's been picking up all the liquid agent coming back here into the bypass chamber. And there is a fresh gas flow coming through the bypass chamber, which is diluting this lethal concentration of gas coming from the vaporizing chamber and then giving you a safe anesthetic concentration. So this is done by means of a splitting ratio. What is a splitting ratio? It's very simple. It is the ratio of fresh gas divided between the bypass chamber, right? This bypass chamber and this vaporizing chamber. And it depends on the dial setting and it also depends on, it's also determined by the saturated vapor pressure. So you can see there are various agents we use commonly, halothane, isoflurane, and sevoflurane. And see, as you increase the dial concentration, right, what is happening here? More gas is entering the vaporizing chamber and it is picking up more and more vapor. You can see, suppose here I'm putting 47 ml of fresh gas flow. Suppose I'm using halogen. And here I put around 47 ml of, I hope you can see my cursor. Yeah, there it is. So here you're putting 47 ml of fresh gas flow of halogen. So 46 will go through the bypass chamber, right? And only about 1 ml will go through the vaporizing chamber, so that the concentration of halogen that you're getting is around 1%. This is the meaning of the splitting ratio 46:1, right? And as the dial concentration increases, you can see more and more gas enters the vaporizing chamber and picks up more and more vapor. So now we talk about, you've understood about the variable bypass vaporizer, and now I'm going to tell you about the measured flow vaporizer. So in order to understand the measured flow vaporizer, just look at this diagram. It's a really beautiful diagram, which is showing you the copper kettle, right? Now, this is the first vintage diagram of the copper kettle, which I found on the net, and it's the first commercial prototype. The trials began in the University of Wisconsin in September 1948. And it was actually very ingenious. And I'll explain what happens here. Now, when we talk about a measure for vaporizer, remember, there are two independent systems here, right? From here, fresh gas flow is coming, right? It's going through an independent flow meter and into the gas outlet. Then a specified amount of anesthetic agent is coming through this limb and it is going again into the vaporizer. It is getting saturated or it is bubbling through because this is a copper kettle. And then when it picks up all the vapor from the copper kettle, see the arrows are red now, then again it goes out into the outlet and into the gas outlet, and an independent regulator of oxygen or fresh gas, whatever fresh gas it is, it can be air, it can be oxygen, there is an independent regulator which dilutes this gas or this vapor which was coming out. An independent regulator dilutes it, and then finally this diluted portion comes out of the gas outlet. So what is the problem in this? The problem is that it's very cumbersome to calculate. You have to make long calculations, and there is also a margin of error. In the variable bypass, it's easy. You fix the splitting ratio, you set the dial concentration, and you will get the desired output, right? So that is the difference between the measured flow vaporizer, which is a copper kettle, and the variable bypass vaporizer. So what is the vaporization method of the copper kettle? It is bubble through. It is a measured flow vaporizer, regulation of output. The temperature compensation is supplied heat. It is kept in a water bath, or it has a splintered bronze disc, and this conducts heat to generate the splintered bronze disc inside. This is what conducts heat. So here you can see, excuse me, that is not working. What will happen is that inside you have a chamber here, right? I'll just explain it on this itself. Gas will come inside, it will go up, and then it will go down into the splintered bronze disc. Here, heating will occur, or temperature compensation will occur, and it is a multiple agent vaporizer, as you know. This is all about the copper kettle you need to know. Now, when we talk about temperature compensation, right? So just you should remember these 4 or 5 classifications, where you have automatic thermocompensation, which we normally do in our OTs. Most of the vaporizers we are using, good for us actually, fortunate for us, that they are automatically thermocompensated. So that you have the TEC, which has a bimetallic strip, Vapor 19.1, which have fluid filled rods, EMO, which has ether filled bellows, the pendant vaporizer, which has fluid filled bellows, and other mercury expansion devices as well. Manual thermocompensation is done by the copper kettle. Supplied heat electronically is the TEC 6 vaporizer. All of you are well aware of it, and we'll just discuss it in detail. It's very interesting. Electronic heat is the Aladin cassette vaporizer, where electronically the temperature is compensated. And there are certain vaporizers which have no thermocompensation, which are the Boyle's bottle and the Goldman's, two which you can remember easily. Now, what is temperature compensation? What happens is that, again, see, again and again this diagram will come. It's good if you have it fixed in your head. This is the bypass chamber. This is the vaporizing chamber. Now, here at the outlet of the vaporizing chamber, there is a bimetallic strip, which is made up of two metals. What happens is that when the temperature changes, this bimetallic strip curves. So, as the vaporization continues, there is a fall in temperature. Obviously, because the liquid is losing heat, it is cooling down, and the vaporizer output is also going down. So there is a fall in the temperature of the liquid, and this is sensed by the bimetallic strip. This bimetallic strip then changes its curvature, right? So if I go back to the earlier slide, you see it was like this earlier, and there was an aperture here. Now the bimetallic strip, because the vaporization is occurring and it is cooling down the vapor is cooling down, the bimetallic strip changes its curvature, and there is a reduction in the aperture. So what happens then? More and more gas goes into the vaporizing chamber instead of the bypass chamber to increase this output. So this is a very nice and ingenious way to compensate for the fall in vaporizer output due to temperature. Then there is also a bimetallic arrangement where there are two rods. The inner rod is made up of invar, which is a relatively non-expansile material. I'm sorry, excuse me. Inner rod is made up of invar. It's a relatively non-expansile material. And the outer jacket here, that's in contact with the vaporizing liquid, and it's also made up of an expansile metal called brass. So outside it's expansile, inside it's non-expansile. And again, whenever there is a disparity in the temperature, it again changes its curvature, it reduces the aperture, more and more liquid goes into the vaporizing chamber, and the vaporizer output concentration is. Now, a question which most students ask me is that, ma'am, why do we have to remember all these old vaporizers? What is the need? We are not using them anymore. So for that, the answer I will give you to that question is that the only reason we need to look behind is to see how far we have come. And this is a photograph of my son. And the reason I put this photograph here is, one, to break the monotony, and second, because he very kindly allowed me to make this PPT and sat with me through patiently. So I'm sharing his photograph. I would call all these historical methods of anesthesia as vintage anesthesia, right? So you have the Schimmelbusch mask, you have the Yonko mask, you have the Murray's mask here, you have the Popper's mask, right? So it was a very crude method of vaporization where this was open drop anesthesia, right? Patient is lying, you're just putting a gauze, you're putting the mask, and you're calculating drop by drop the amount of. For ether, it was around, I think, 16 drops per surface area, and for chloroform, it's around 12 drops. So this was a very crude method wherein sometimes an inadvertent amount of lethal anesthesia was administered to certain patients. Now about the EMO vaporizer. Now I'll just explain this very, very briefly because first of all, now you are pros and you will be able to tell me the classification of the EMO vaporizer. So this is what? It's a concentration calibrated vaporizer. What is the vaporization method? It's flow over with wick, right? And its temperature compensated by supplied heat. It is definitely agent specific because it is only using ether. It is a draw over vaporizer. I'll explain to you what a draw over vaporizer means and what is the difference between draw over and plenum. And it can be used in circuit as well as out of circuit. So earlier, as I told you, let's just talk a little bit, 5 minutes about the history, right? A simple piece of cloth was used as a vaporizer. And the anesthesia was being administered then as well. But then there was the first casualty in anesthesia, a patient named Hannah Green. And scientists and anesthetists realized that the success of a good anesthetic procedure means that you administer precise concentration of vaporizer throughout, irrespective of the atmosphere. And this dictum holds true even today. That is actually the successful outcome of a good anesthetic procedure. So in 1950, Professor McIntosh designed the Epstein-McIntosh Oxford Vaporizer. Epstein was the physicist who helped to build it. McIntosh was Professor McIntosh himself in Oxford University. So that is about the EMO vaporizer, and this is also a variable bypass vaporizer, and it is a draw over vaporizer. A draw over means that air is drawn by the patient's effort over an either filled chamber, and if the patient has an adequate respiratory effort, suppose the patient has a good respiratory effort, then it also has a valve, and if the patient has a good respiratory effort, then the valve can be inactivated by a magnet. And the temperature compensation is done by either filled bellows. What do? They expand. They expand at room temperature and they contract when the temperature falls, and they maintain an even output, right? So also what happened was that it was placed inside a water bath. So if the temperatures were very cold, then you could use warm water. The water chamber was the thermocompensation technique. And if it could also be used in a very cold environment, you could use antifreeze agent there. And for oxygen supplementation at higher altitudes, Brigadier Rama Rao adapter was added for oxygen enrichment at the inlet. So this is a little about the EMO vaporizer, and this is the Oxford miniature. Sorry, these are the Oxford bellows. I have incorrectly labeled this. Please excuse me. So these are the spring-loaded concertina bellows of 150 ml each, 2 unidirectional flap valves, and a Rama Rao's modification for oxygenation, and a magnet to inactivate the valve as well. Now we come to Goldman's vaporizer. Now, how will you classify Goldman's vaporizer? Goldman's vaporizer is obviously flow over without wick, as we know. It's concentration calibrated. It has Mark 1 and Mark 2 markings, and it's definitely concentration calibrated. The problem is that there is no temperature compensation. It is again multi-agent. Both halothane and trilene can be used, and you can use it both in as well as out of system. So in the classification of vaporizers, we talk about agent specificity as well. So agent specific, like TEC, Vapor 19.1 and Plenum, right? That vaporizer will only hold that agent, specific for halothane, specific for CO, specific for test. Then multiple agents, good example is a Goldman vaporizer. Now we talk about plenum or draw vaporizers. Now plenum, what does plenum mean? Plenum is an Latin term, right? And it means full. The exact meaning of plenum is the opposite of vacuum. In air conditioning terminology, it applies to air that is forced in, cleaned, and temperature adjusted. And it is always designed for a continuous flow of pressurized gas. Remember, P for pressure. Plenum means pressure, plenum means high internal resistance, right? So the plenum vaporizers are all the TEC vaporizers that we use. And the draw over vaporizers, you can use the mnemonic EOG, EMO, that is Epstein-McIntosh Oxford, and OMV vaporizers, Oxford miniature vaporizer, as well as the Goldman's vaporizer. They are draw over vaporizers. So what are these draw over vaporizers? I'll just tell you subsequently. In plenum vaporizers, what happens is that a positive pressure upstream of the vaporizer, like the gas from the flow meter, is pushing the carrier gas through the vaporizer. So the carrier gas is at a higher pressure, and remember, you cannot breathe through these vaporizers. They are high resistance vaporizers. In draw over vaporizers, they are low resistance vaporizers. The patient's inspiratory effort pours the carrier gas through the vaporizing chamber. A sub-atmospheric pressure may be developed in the gas downstream to the vaporizer, and this draws the gas through. It requires the patient's respiratory effort or some mechanical means. EMO is a good example of a draw over vaporizer. Here you can see draw over vaporizer. It can be used with a bellow as well as without a bellow. So in the last point in the classification of vaporizers, we talk about location. So vaporizers can be out of circuit, that is, which we normally use. TEC, Penland, Aladin, all the vaporizers we use are out of circuit. In-circuit vaporizers are nowadays almost obsolete, but I will tell you exactly how it means. Now, these two diagrams, just concentrate on these two diagrams, right? See, this is a vaporizer which is out of circuit. Normally, the vaporizer we use. So imagine that this vaporizer is mounted at the back bar of your anesthesia machine. It could be halothane, it could be silver, whatever. And the gas now goes into the, sorry, excuse me. The gas now goes into the circle system, right? It goes into the bag, it goes into the CO2 absorber, it goes into the patient tent, right? It picks up the vapor, picks up all the vapor from here, and it goes back into the CO2 absorber. It is going into the circle system here, right? What happens inside the circuit? Now, just concentrate here. What happens here is that the vaporizer is in the circuit, right? So what is happening here, that here the fresh gas flow which was circulating was devoid of the vapor because the vaporizer is adding a requisite amount of vapor to the circle system. But the fresh gas flow coming back is devoid of the vapor. What is happening here is that because the vaporizer is in the circuit, once fresh gas flow goes, it carries some amount of vapor into the bag, and then it is absorbed along with the CO2. Then it's picked up by the patient. It goes back into the CO2 absorber. When it is picked up by the patient expires the air, and the expired air of the patient now also carries some amount of vaporizer back into the CO2 absorber. So what is happening here is that the fresh gas flow which is coming back from the patient, that is also containing some amount of vapor in the vaporizer insert, right? Now then, two things you have to remember. I've simplified this for you because this is an MCQ also, and this is asked often in Vivas, and sometimes you make a mistake because you forget. Ulta bol dete hain. Pumping to pressurizing or pressurizing to pumping. So remember, whenever you apply any positive pressure, like I'm pressing the bag here in the Gauzy system, or maybe I'm giving an oxygen flush of around 60 psi, what will happen? The pressure will increase, and it will increase to a considerable amount. So whenever the vaporizer output concentration increases, right, it is pumping effect. And whenever vaporization output concentration decreases, it is pressurizing effect. Remember this flow chart I've made it for you, right? Now let's understand how it happens exactly. What is happening? Suppose you have a gas, again, the same diagram again. So now you're quite well versed with it. Gas is coming from the inlet to the bypass to the vaporizing chamber. What did I do here? I applied pressure here, either by pressing the oxygen flush or by pressing the bellows. I applied a considerable amount of pressure here. So what will happen now? Let's look at the other diagram. This portion of this vaporizing chamber is known as the inlet of the vaporizing chamber. It is not the inlet here. This is the inlet of the vaporizer. ये जो part है, this is the inlet of the vaporizing chamber. So जब हमने pressure pumping effect लगाया, यहाँ पे pressure लगाया, so the gas came back into the chamber. It picked up a lot of vapors from the vaporizing chamber, and it went back into the inlet of the vaporizing chamber. And from here, now this gas which had come into the inlet of the vaporizing chamber is saturated with vapor. And the problem is that this gas is now carrying this vapor into the bypass chamber as well, which is prohibited. Ideally, you don't need vapors in the bypass chamber, right? Bypass chamber is only for fresh gas flow, but what happens in the pumping effect? Because of the pressure and because of the back pressure, lots of vapor is picked up. It all accumulates in the inlet here, and then boiler, it's coming back into the bypass chamber. And this is something which we don't need, right? So pumping effect कब कब होता है, right? How do you remember it? Remember there are 3 lows and 2 highs. So what are the 3 lows? If there is a low fresh gas flow rate, right, then you might have the pumping effect. Then low liquid level in the vaporizing chamber. Maybe you forgot to fill, or the technician forgot to fill the liquid in the vaporizing chamber. Then at lower dial settings, this happens. Then high peak pressures. Maybe you forgot to open the APL valve. You forgot to open the APL valve. So that is high peak pressure. So the patient is getting light. And frequent change in pressure. Again and again, you are pressing the oxygen flush. Again and again, you are pressing the bag. So in that case, there will be the pumping effect. So We know the problem. How will we solve the problem? So you can do this in two ways. You can make alterations to the vaporizer and you can make alterations to the anesthesia machine. So to make alterations to the vaporizer, you decrease the size of the vaporizing chamber, right? You increase the length of the inlet to the vaporizing chamber, which I mentioned earlier. Then you can remove the wicks from the entry point in the vaporizing chamber so that more vapor is not absorbed there. Increase the resistance, of course. And for the anesthesia machine, you can put a check valve downstream that will solve all your problems. Now the pressurizing effect. Now one thing remember, right? Basic thing you have to remember, difference between pumping and pressurizing effect. Pumping effect occurs at low flows. Pressurizing effect occurs at high flows, higher flows. Kitna flow? Around 15 liters per minute. So when there is earlier scenario where the flow was too low. In this scenario, the flow is too high. So what happens when the flow is very high? Lots of fresh gas enters the vaporizing chamber. And the number of molecules which can saturate that large amount of fresh gas that is entering is not so much. So what happens is that the output is low, right? So pressurizing effect is affected by high flow rates, low dial settings, and large pressure fluctuations. So the previous two things are the same as in pumping effect. The only difference is between high flow rates and low flow rates, right? If most of you who are sleeping by now, because we have a lot left, please, if you are in this state, please concentrate again. I'll come to the Tech 1 and the Tech 2 vaporizers. See, we don't use them as such. So I'm just going to touch them very briefly. They are all concentration calibrated, flow over with wicks, right? Temperature compensated vaporizers. They are agent specific. They are plenum vaporizers. Remember, all of them are now plenum, right? And they are all out of circuit vaporizers. What is the difference between 1 and 2, remember? In Tech 2, remember, it's round with a capacity of 150 ml. Here you have a 70 ml capacity. Here you have one bypass. Here you have around two bypasses. There is an effect of back pressure in the Tech 2 vaporizer, which was overcome by the Tech 3 vaporizer. The accuracy is definitely more in Tech 3. The calibration in Tech 3 is around 5%. The main difference here is that the bimetallic strip in Tech 2 is present in the vaporizing chamber, and here it is present in the bypass, right? Now we come to Tech 4 and Tech 5. Again, this is what you have to tell the examiner again and again. How will you classify the vaporizer? So by now we have to remember this, which I just taught you. Sorry. So this is again vaporization method. It is a flow over vaporizer. It's a variable bypass, concentration calibrated because you are setting the concentration. How do you temperature compensate? By automatic thermocompensation. There is a bimetallic strip inside, as I told you. It's definitely agent specific. So it's purple for isoflurane and it is red for halothane. And it is a high resistance plenum vaporizer out of circuit. Differences between Tech 4 and Tech 5. Tech 5 has a larger capacity, remember. It's a bigger vaporizer than Tech 4. Take a look. Tech 5 is a bigger vaporizer than Tech 4. And then the thermostat here, remember the main thing. Even if you don't remember how much ml when the wicks are dry and 100 ml when the wicks are wet, if you don't remember these technical details, just remember that here the wicks are more saturated with vapor. Here the thermostat is present in the center of the vaporizer and here it is at the base. In the concentration control dial, here it's a little complicated, as you can see. It's a little complicated, but here it's user-friendly. So they've made it more user-friendly. And accuracy, definitely, as the vaporizers progress in their generation, they become more and more accurate. Service, annual or biannually is required. Now, modern vaporizers, what do we require in modern vaporizers? The vaporizers we are using, what is our goal and what is our aim? They should be precise, right? They should be absolutely precise. So the dial settings and the output should match perfectly. They should be agent specific and flow stabilized. They should perform equally well over a wide range of flows, right? And the vaporizing chamber should incorporate a network of internal channels or wicks, which ensures that all the gas that is emerging is fully saturated with the vapor, is fully utilized all the vapor that is coming inside. It is literally soaking it up. So this is what we know as called precision vaporizers, or the tech vaporizers that we use. I'm going to explain in detail to you the tech 5 vaporizer, right? Because if you understand this, you will be able to understand every vaporizer that you encounter. Just concentrate. One by one we'll take it. Let me see if my pointer is working. So the first is the vaporizer inlet, as you can see, right? This number 1 here, this is the vaporizer inlet. Number 2 is the IPPV assembly. Then there is a long, large assembly, which is a hurdle here, which the gas has to encounter when it enters the vaporizer. So this is the first hurdle. And the second hurdle, number 3, you see here are the helical wicks. And you can see that they are more saturated at the bottom and they are less saturated at the top. 4, everybody knows what 4 is. 4 is nothing but the liquid agent inside the vaporizing chamber. And then 5 is your rotatory valve, right? Here I told you that the bimetallic strip is present in the bypass chamber, right? This is the vaporizing chamber inside. And outside here you have the bypass chamber. So the bimetallic strip here, sorry, the bimetallic strip here, you can see it here. This is present in the bypass chamber, right? And then 7 here you have a mixing chamber where they both mix. And then this is the output. So clear, these are the parts of the vaporizer. The inlet, the IPPV assembly, the wicks, the helical wicks, the liquid agent, the concentration rotatory valve or the concentration dial, and here is the mixing chamber and the outlet. Right. Now let's see how it works. Now, when you move this dial, what will happen? According to the splitting ratio, the gas will be divided into 2 parts, right? A part of the gas, you can see the blue arrows here. This will go inside the bypass chamber, right? And another part of the gas is now going to enter the vaporizing chamber. So when it enters the vaporizing chamber, first it will encounter this assembly inside. It will have to traverse this path, and then it will encounter these wicks. Now these are continuous wicks, right? The cross section decline. Actually, they are a continuous, a maze of wicks. It's going through these wicks, soaking it all up. It's going inside the vaporizing chamber, soaking up everything, and then it is coming out and getting mixed here in the mixing chamber, and then it is being delivered to the patient. This is what you actually see. I've just taken this diagram so that you can actually visualize what's happening inside the Tech 5 vaporizer, right? So the blue arrows here again, this is the fresh gas that came here down, you can see. This is the bypass chamber going out and out and out and out. And then these purple arrows are the splitting, according to the splitting ratio. Some of the gas has gone into the vaporizing chamber. Here it has encountered all the wicks, the helical wicks. It has encountered the IPPV assembly. This is the place where there is the liquid of the vaporizing chamber. It gets soaked up and then it goes back up into the mixing chamber, and then it is delivered to the patient. In the Tech 5 vaporizer, you can see a control dial on top. You actually touch the control dial. There are 2 things which you have to remember here. There is a release button at the rear of the dial, right? And there is a locking lever. So दो चीजें in the Tech 5 vaporizer. There is a control dial, there is a release button, and there is a locking lever. And apart from that, you also have a side glass where you can see how much of vaporizer you have filled. See? Now, what's important in Tech 5 vaporizer is filling devices, right? Filling devices are nothing but a lock and key mechanism. You see, this is the vaporizer inlet. Can you see the vaporizer inlet here? And this is the filling tube. So this is purple for isoflurane and this is red for halothane. And the configuration is such, right, that these precisely fit into these vaporizer inlet. It's a lock and key mechanism. And how do you fill it? The reason I'm stressing on this is that it's very important for you to know this. How do you exactly fill the vaporizer? So here you can see this is your filler tube. This is the locking lever, this blue triangular thing, it will come down, right? This is going to come down, right? Once you fill this, you niche aa jayega. You will attach this tube over here. Open this. Once you open this, this will be a continuous tube where you can fill from the bottle through this tube. You can fill the whole vaporizer. And here in the side glass, you you can see how much it has been filled, right? Then there are some other vaporizers which we use and they are present on some of our anesthesia trolleys. That is the Draeger 19.1 vaporizer. If you've understood the tech vaporizer, it's very easy for you to understand the Draeger 19.1 mechanism as well, right? So let's classify it first. Obviously, it's a flow over variable bypass. Now, by now you're a pro, I'm sure. It's a flow over variable bypass, concentration calibrated vaporizer with obviously an automatic thermocompensation. Here you have a metal rod, not a bimetallic strip. Okay. And it is agent specific. It is a plenum out of circuit vaporizer. So again, you can see it's the same concept again. You have a bypass chamber, you have a vaporizing chamber, and you have a pressure compensator here, which is a new thing in the 19.1 Draeger vaporizer. You have a pressure compensator. It goes into the vaporizing chamber, gets saturated, comes back into the bypass chamber and into the mixing chamber and the fresh gas outlet. It goes, right? And number 8 is the expansion element or the temperature compensation or the rod that is used, which is made up of two materials which are of different thermal conductivities. This is the Draeger Vapor 2000, which often we use, right? And again, this is also a flow over variable bypass, because I'm repeating this again and again because this is how you have to tell every vaporizer in your exam. It's variable bypass, concentration calibrated, automatic thermocompensation, agent specific, out of circuit Plenum vaporizer. Remember, it has a T mode here, right? A transport mode. That's what you have to remember now. This is a Tech 7 vaporizer. We all know Tech 7. Very easy to, again, classify. Exactly the same as what I mentioned earlier. What's different in Tech 7 is that there are a lot of wide selection of filler assemblies here in Tech 7. So, and it's much easier. You don't have to follow that 5-step you followed in Tech 5. It's much simpler to fill the Tech 7 vaporizer. Now, this is something, it's a concept which you must understand, and it's a very, very important concept, I feel. So what I'm trying to explain to you here is Select-a-tec Vapouriser. Like, you should only be able to use one vaporizer at a time. Yahan pe, what are we seeing in this picture? We are seeing the back side of the vaporizer, right? Suppose this is the manifold bypass. Here you have the percentage control dials. There is an extension rod here in a vaporizer, right? I have marked it in orange so that you can clearly see it. And what happens is that whenever you activate the release button, or whenever you press this, when you press this dial, right, this extension rod, it extends laterally outwards. And when it extends laterally outwards, it does not allow the second vaporizer to expand sideways. It does not allow any space for the second vaporizer to fit into this manifold bypass, right? And that is how you can use only one vaporizer at the time, and that is the safety mechanism here. So here you can see that this fresh gas flow that is coming, it will just go back out into the manifold bypass. If you switch on the vaporizer, then and only then will this gas come inside this vaporizer and get saturated by it, right? So it has two parts. It can go piche seedhe through the manifold, or it can get saturated with vapor through the vaporizer. Now just imagine this. This is a schematic representation of two vaporizers, right? So here both the vaporizers are off and no fresh gas is entering any of the vaporizers. Now what happened here is this vaporizer is off. The fresh gas has entered into vaporizer number 2 because here you see this rod has extended laterally sideways. It's not there in this picture. It has locked off this vaporizer 1, and now all the gas will come inside this vaporizer 2 back into the machine outlet, if you can follow my cursor. So here, this is exactly what I told you. You can see it specifically on Tech 7, how the gas is coming in and out of the vaporizer. This is the small lateral rod that fits into this hole, and this is how it locks up one vaporizer at a time so that you can use only one vaporizer at a time. This is a Draeger interlocking system. It is for all the vaporizers. Suppose we have three vaporizers like halothane, enflurane, and isoflurane, and we have switched on isoflurane. So what is going to happen is that these rods, they will change their shape, they will alter their configuration in such a way that only halothane can be used. The rest are locked. Can you see? Halothane can be used here. This port is open, but the port of enflurane, the port of halothane has been completely sealed by the configuration of these interlocking rods. So this is how the Draeger interlocking system works. I'm sure most of you are bored, but a few very important topics are left. Let's just proceed. Bear with me a little more. A very, very important vaporizer which we used. And this is a X6 vaporizer. Now all is not so easy. The classification that I was rattling off has changed a little bit. This is a saturated vapor generator. It is an injection type of vaporizer, regulation of output. It is supplied heat. Obviously, it is agent specific for Desflurane. It is a high resistance plenum vaporizer which is used on the circuit. So what happens in a Tech 6 vaporizer? Actually, this is switched on automatically, right? And once it is switched on, it requires around 5 to 10 minutes of warm-up time, during which it can be turned on. One interesting thing I'd like to tell you about Tech 6 vaporizer is how the number 6 interplays here, right? Number of fluorine atoms is 6, right? The saturated vapor pressure again is around 669, I feel, but I have just for memory purpose, I will put it as 666. And the boiling point again is 24, so again 6 4s are 24. Again 6 is coming into play. The Mach percentage is 6. Oil gas partition coefficient is 18, which is again multiplier of 6. And the concentration dial has graduations of 1%, right? But 10 to 18%, you have 2% increments, but there is a stop at 12%. So you have to manually override that stop. So once you reach 12%, what happens is that you are actually conscious. The reason this has been done is that you are actually conscious that, oh, I'm giving an output which is more than 12% and I have to be careful for the patient. This is actually a safety mechanism that has been incorporated into this Tech 6 vaporizer. Filling the vaporizer is very easy. You can fill it even while the vaporizer is in use, as you see, right? And why does it need to be heated? Now, this is a very good question. What happens is that the boiling point of this vaporizer is 22.8. That is, it is boiling at room temperature and it is highly volatile. So if you look at this graph, right, it's a very nice graph which is comparing all the various anesthetic agents. So it's pressure against temperature, as you see, and you can say that 1 degree drop in temperature for Desflurane, even 1 degree drop in temperature, the drop in saturated vapor pressure is much, much higher as compared to the other anesthetic agents like halothane, like sevoflurane. So for Desflurane, a 1 degree drop in temperature will give you a far significant drop in saturated vapor pressure. So in order to maintain precision, you have to heat it. So this is a schematic diagram. It's a simple diagram. You don't have to be very intimidated by it. Simple, let's see, the gas is coming inside from the flow meter. Here it is being heated by the Desflurane heater, right? It's going out through the flow control valve. And here you have fresh gas flow and a flow resistor. So what does this flow resistor do here? What it's doing is that if there is a large amount of fresh gas flow, right, mostly uneconomical to the patient. So this flow resistor is, according to the dial concentration which has been set, diluting that and bringing it down by incorporating a flow resistor. That's all. And then out into the fresh gas outlet, you get the required dial output. Now we come to the next topic, which is an Aladin cassette vaporizer. If you look at this Aladin cassette, when I started reading vaporizers, I did not know that Aladin cassette is now a second generation also. But now we have not only a first generation, but a second generation Aladin cassette as well. So it is color coded, as you know, it is yellow in sevoflurane, and it is purple in iso, and it is blue in Desflurane. and it can be used in the Datex Ameda or the GE ACES anesthesia workstation. The difference between, now let's just talk about the parts a bit. I'll just show it to you here. Here you have the chamber or the agent chamber. This is the eject handle. This is where you hold the vaporizer actually. And then you have a key filling system, which you can see over here. This is a key filling system right here. You can see a small black hole. That's the key filling system. Then you have a liquid level indicator. And finally, here you have, this is not a dial. Aladin cassette vaporizer is very difficult for most of you. So what I've done is I've given you this basic diagram, right? This is a basic diagram which you all know. And I will now superimpose the Aladin cassette on it so that you can understand it fully, right? Now just see, same as you know, this is your fresh gas flow inlet, your bypass chamber, your vaporizing chamber inlet, chamber outlet, and the common gas outlet. What did I do here? I've added a lot of things, but there is no need to get intimidated by anything. It's all very, very, very simple, right? So what happens is that again, FGF yahan se aa raha hai, just follow my cursor. FGF is coming right through the inflow meter. There is a one-way valve here. That's fine. Nothing to worry about. It's coming inside, right? It's going into the cassette. Now there is an inflow check valve here, just outside the cassette, and an outflow check valve. So these check valves, right, they only when the cassette is mounted, then they open. Yeah. So they open only when the cassette is mounted, these two check valves. And what else do you see here? You see a temperature cassette sensor. Now, what is this temperature cassette sensor? It's actually something that senses the temperature and gives you an adequate idea. And here you have your cassette ID. So here you have your cassette ID as well. The liquid is bubbling through. You have your temperature sensor. You have an outflow check valve. And before you go through this pathway, right, after the vaporization, you're going out into the common gas outlet. Just let's come here a bit and see that there is a pressure cassette sensor here. What happens is that if there is a large amount of pressure coming in through the vaporizer, this pressure cassette sensor, it nullifies the pressure, and through this scavenging system and a pressure relief valve, it releases the pressure out, right? So it's exactly the same as a basic vaporizer, but it's got lots of little nice ingenious devices which make it very precise. Now, there is a proportional flow valve which will give you an exact precise amount of vaporizer that is flowing through this. And these inflow flow meters in both the sides, they are connected to the CPU of this FNF, the large FNF, capital FNF that you're seeing here. This is connected to the CPU of the Aladin cassette, and here also you have a manifold temperature sensor. So the basic design is the same, but you have incorporated a number of ingenious devices to make it more precise. This is what the internal structure of the Aladin cassette looks like. Here is the cassette, the ejector and all the parts that I told you before. Here is the filling system, the identification magnets. And here you can see the beautiful wicks. You can imagine how beautifully it is saturated with paper. And inside here, this orange structure that you see inside here, this is the temperature sensor strip, right? And this is the locking mechanism. So this is actually how it looks like. And this is a schematic representation, which I just talked about. The last few slides I would like to tell you are about Anaconda or anesthetic conserving device. Here you can use a vaporizer. For example, if you want to use it in the ICU for an intubated patient, you can use this vaporizer without actually using the anesthesia machine. You have to just attach it between the endotracheal tube and the Y piece or the Y connector. And one part of this tube goes into the volatile agent syringe pump, which is present here. And this is the heat or the temperature rod here or the compensator here. And it is a very useful device which is being used in ICUs. And I'm sure that you must have seen this device somewhere. Now about the safety features, this is what is going to be asked to you in your exam. And I've discussed Select-a-tec Vaporisers, how to mount one vaporizer, So throughout this entire presentation, I've discussed the safety features. I'm just going to re-enumerate them and recapitulate. The important safety features here include a color specific for each agent, the keyed so the filler bottles, a low filling port, right? Only one vaporizer should be turned on, and the gas should enter only the vaporizer which is turned on, right? Then the vapor output is minimized when the vaporizer is off. And the vaporizers should be completely locked into the gas circuit and they should be sealed completely correctly, right? Remember that the concentration dial increases output when it is rotated counterclockwise. Now, the last slide that we will discuss is the slide of hazards, right? Now, what is the first hazard that can occur? Tipping. What happens in tipping? If suppose you tip it more than 45 degrees, so the outlet valves will be obstructed, right? And then how will you rectify this? You will flush it for 20 to 30 minutes at high flows, and then this at rates which are higher than the dial concentration. Overfilling can also occur. Overfilling will lead to a high output concentration. Leaks can occur. Leaks are very common if you don't mount the vaporizer properly on the manifold, then leaks can occur, and it's a very common thing to occur. So for this, you have to do a negative pressure check, right? Misfilling, which is hardly now possible because they are all keyed vaporizers. Contamination, if you used a contaminated agent and you put into the vaporizer, then it can get contaminated definitely. And underfilling can occur if you have not filled the vaporizer properly and you will simultaneously inhale another anesthetic. This is a hazard, but it is not possible with the modern vaporizers because there are so many safety mechanics. So this is the last slide. Finally, we have finished this long topic of vaporizers. And thank you all for your attention.